thank you very much for the invitation, and also thank you very much for all this organization in these very special circumstances. And so I will talk about this kind of submanifolds. This is a joint work with Matias Navarro and Didier Solis, also from Mexico. And here is the plan of the talk. I will give some basic facts on null submanifolds. In particular, I will talk about this screen distribution technique to study them. And I will give three kinds of results. Some results on totally umbilical null hypersurfaces. Also, I will speak about submanifolds with screen parallel shape operators. I will define them in a minute. And also in the final part of my talk, I will speak about the isometric immersion problem for null submanifolds. This last part is some work in progress. Okay. So 2 or 3 slides for non-specialists. We say that a scalar product on a vector space is a symmetric bilinear form, which is not degenerate. That means geometrically is that if there is some vector which is orthogonal to all other vectors in the vector space, then U is equal to 0. And the standard example is that scalar product on Rn. Also, we define a semi-Riemannian manifold as a differential manifold with some semi-Riemannian metric. That is, we choose for each point in the manifold and a scalar product in this sense, which varies smoothly. And that means, in particular, that it has constant index. Also, if we have a submanifold, it is semi-Riemannian if the restriction of the metric to the tangent space of the submanifold is non-degenerate. The standard examples here are the so-called Lorentzian space forms, which are the Lorentz-Minkowski space with this metric here, the de Sitter space, which can be seen as the unit sphere in the Lorentzian-Minkowski space, and also the pseudo hyperbolic or anti-de Sitter space, which can be seen as also as a quadric in some pseudo-Euclidean space. Well, I think that almost everybody knows that the geometry of semi-Riemannian manifolds works perfectly fine, as in the case of Riemannian geometry. We have Levi-Civita connections, curvature tensors, geodesics, and so. In particular, the Lorentzian space forms are those which have constant sectional curvature. But as we said in the title of the talk, we want to study null manifolds. And of course, the motivation for this study comes mainly from physics. We have, for example, the light cone in the Lorentz-Minkowski space, which is given as in the slide. And also, we have several kinds of horizons. And in the smooth part of these horizons, they are also null or degenerate manifolds. So it is important to study them in some way. And we want to study this kind of objects from the geometric point of view. So which will be our context? It can be done this in the semi-Riemannian case, but to simplify notation and those things, I will speak about null manifolds on Lorentzian manifolds. So M bar will be a Lorentzian manifold, and that is a differential manifold with a metric G bar of constant index 1. M will be a hypersurface such that the restriction G of the metric G bar to each tangent space is degenerate, and we call them null, a null hypersurface. The fact of the restriction of the metric being degenerate is equivalent for giving locally a vector field psi different from 0, which is both tangent and normal to M. This vector field psi generates a bundle, a one-dimensional bundle called the radical bundle, as in the graphic here. So our last reminder of the Riemannian case, of course, if M bar is a Riemannian manifold and M is a hypersurface, we know that the Levi-Civita connection nabla bar of M bar can be decomposed into its tangent and normal parts, and we give the usual decomposition like in the slide. And nabla bar can be decomposed also in the tangent and normal part, and the tangent part of the Levi-Civita connection is the Levi-Civita connection of M. So this decomposition cannot be made in the degenerate case because the tangent part and the orthogonal part have intersection different from 0. Okay. So what can be done in this case? Since we already have a privileged direction defined by this vector field psi, it is easy to study what happens with the geometry in that direction. So it is natural to choose for each point a subspace of the tangent space of M, complementary to this direction psi, and use the subspace to study the geometry of M. This subspace is like projecting onto some screen or something like that. And instead of expressing our concepts in terms of some manifolds, we will begin expressing them in terms of distributions. So we have this definition. We say that a screen distribution on M is a distribution S of Gm complementary to the radical, or say to the bundle spanned by the vector field psi. And we will hereafter choose a fixed screen distribution, and we will denote the null hypersurface by these three elements, M, G, and S of Tm. Okay, so we know that for each screen distribution, there is a vector field Tr called the transversal bundle, such that it satisfies these conditions on the scalar product here. The last two conditions, g bar of nn equal to 0 and g bar nx equal to 0, mean that n is a null vector field, which is orthogonal to each vector field in the screen distribution. And the first one, g bar of psi n equal to 1, can be seen just an normalization of this vector field. So these vector fields are defined locally, but we will work in a neighborhood or an open set where these two vector fields exist. Okay, we have this picture here. Also, we have M is the surface, and we have this vector field Xi generating the radical bundle. We have N generating this transversal bundle. And now we have this the compositions of the tangent bundle of M bar as the direct sum of Tm and the transversal bundle, and also the tangent bundle of M can be decomposed as the screen distribution plus the radical bundle. Okay. So we have this decomposition for the tangent bundle of M bar. And for some formulas, we will use P as the projection of the sections of Tm over the sections over the screen distribution, using this decomposition. So now we have all elements to do some geometry. We have nabla bar, the Levi-Civita connection of M bar, and we have this kind of Gauss-Weingarten equations where let's say that since we have two decompositions here, we have a pair of or four Gauss-Weingarten equations in these forms. And also we have a lot of linear connections. We have 4 linear connections on all these bundles. And we have H and H star, 2 second fundamental forms. And most important, AN and AXI star are 2 shape operators. In this context, we have these 2 local shape operators. Okay, so we want to study the geometry by means of these elements. We also have, of course, since we have these connections, nabla, which is the connection on M, nabla star, which is the connection on the screen distribution. We have also the curvature tensors R and R star, and we have some kind of Gauss equation like in the slide. And later on, we will suppose that our ambient space M bar has constant curvature C bar. So what can be done with these elements? Since we have 2 shape operators, it is natural to impose some kind of relation between them. So Atindogbe and Dugal suppose that the shape operators are linearly related. So we say that a null hypersurface is screen conformal if we have this condition in the definition. One of the shape operators is a multiple of the other one. And they show that this condition is a very nice condition for studying the geometry of a null hypersurface. For example, they proved this theorem. Just recall that M is totally umbilical if and only if the second fundamental form B is a multiple of the metric. Okay, so the theorem is as follows. We have a null screen conformal hypersurface. Then the screen distribution is integrable, and the null hypersurface M is totally geodesic or umbilical in M bar if and only if each leaf M prime of the screen distribution is also a totally geodesic or totally umbilical, so manifold of dimension 2 in M bar. So under these conditions, the geometry of the leaves of the screen distribution reflect the geometry of the null hypersurface. Navarro, Solis, and myself, we observed that this definition of screen conformal hypersurfaces is important, but it can be extended in some way that I will speak about in a minute. Just let me give an example of all these kind of things. We just remember that a manifold M bar is a generalized Robertson-Walker space if it is a Lorentzian warp product where I is a real interval with a metric minus dt squared, and F is a Riemannian manifold, and the metric of F is warped by a function rho, in the sense that we have below. The metric of our space is minus dt squared plus rho square gf. Okay. So in this context, a classical Robertson-Walker space is such a space where the fiber F has constant sectional curvature. And more important, the Lorentzian space forms are examples of this kind of warp products. Okay, in this way. So what happens in the context of Robertson-Walker spacetimes? We have that the null hypersurfaces can be seen as a graph of a function in the way that appears in the proposition, and this function is a transnormal function, which means that the norm of the gradient of f is f composed with this warping function. In this case, we can give an explicit expression for our vector field psi spanning the radical bundle, and the vector field n spanning the transversal bundle, and do some calculations. So we may see that the shape operators are related by the equation here in red. So where P is the projection that I defined before. So they are not linearly related, but they satisfy this kind of thing, which we define as the following concept. A null hypersurface is screen quasi-conformal if the shape operators are related in the way that appears in equation 2. And this can happen locally or globally. So in order to work with for example, classical Robertson-Walker space times, we may extend the definition made by Atindogbe and Dugal to this new definition. So it is not a surprise that we may generalize the result on totally umbilical null submanifolds. We proved this theorem in 2018, I think, but it appeared recently. We have a null screen quasi-conformal hypersurface. Then the screen distribution is integrable, and M is totally umbilical in M bar if and only if each leaf of the screen distribution is also totally umbilical as a codimension 2 submanifold of M bar. Okay. So we wanted to use this notion of quasi-conformal null hypersurface to study other kind of submanifolds, which I will define in the following slide. Which are also some kind of classical hypersurfaces. We say that the shape operator xi star is screen parallel if its covariant derivative is 0, but only for x and y vector fields in the screen distribution. This is equivalent to the commutativity of nabla star and hc star in the way that appears in the slide, only for xy in the screen distribution. Okay, and also this notion implies that the curvature tensor R star of each leaf of the screen distribution and our shape operator commute in this sense here. So we wanted to study this kind of null hypersurfaces with screen parallel shape operator. What happens with this notion in the case of Robertson-Walker spaces? We have that the shape operator xc star is screen parallel if the shape operator of each leaf of the screen distribution is also parallel in the classical sense. So using this notion of screen parallel shape operator, we will study also the principal curvatures of our null hypersurface. So we just state the fact that the shape operator a psi star is diagonal, can be diagonalized, And also we know by some calculation that Xi is an eigenvector of eigenvalue 0. And so we have a frame field of eigenvectors E naught to En, so that the last ones, the last n ones, are an orthonormal frame field of the screen distribution. And we call lambda I, the eigenvectors, the screen principal curvature. So what happens if we have a screen parallel shape operator? Well, we have this kind of lemma here, so that the eigenvectors satisfy this expression, which will be very useful. Just note that we only take these eigenvectors different from the eigenvector lambda naught. Okay. So in the case when we have a null hypersurface with a screen parallel shape operator and M is screen quasi-conformal, the expression in the lemma before is like this. And more important, we can use this expression to obtain that our shape operator has at most two different non-zero screen principal curvatures. Okay, so so we have this. We have first the total umbilical case, where all the screen principal curvatures are the same, and we have conditions for having two different non-zero screen principal curvatures. So we will study this case. I just remember our hypothesis. We are in the Lorentzian case, where M bar has constant curvature. M has screen parallel shape operator, is also screen quasi-conformal, and we have two screen principal curvatures different from 0. So we will study this case in the following minutes. We define these distributions T lambda T mu for our eigenvectors. We fix an order. Lambda is always greater than mu. And these distributions have nice properties. They are differentiable. And moreover, if we have all these conditions in the previous slide, then T lambda and T mu are involutive. And also, if the dimension of each of these distributions, if, for example, if T lambda has dimension greater than 1, then we have some kind of technical properties. Just I put in red x of lambda equal to 0, which means that lambda is constant along the distribution, along the leaves of the distribution. And also the same happens with T mu. Moreover, if M is screen conformal, then also we have this condition of the screen principal curvatures being constant along the other directions. No? X of mu is equal to 0, or C of lambda is equal to 0. So we have these conditions in red, meaning that our screen principal curvatures are constant along both distributions, which means that they are both constant along the screen distribution. So we just give a definition. We say that M is a null screen isoparametric hypersurface if the screen principal curvatures are constant along each leaf of the screen distribution. So we just rephrase our discussion before, saying that if we have all these conditions, constant curvature on the ambient space, screen conformal hypersurfaces with screen parallel shape operators, and two non-zero screen principal curvatures with both distributions having dimension greater than 1, then M is null screen isoparametric. So this result gives us also a structure result for this kind of submanifolds. Under all these conditions, we have that M is a product, C times M lambda times mu, where C is a null curve, an integral curve for the vector field psi. M lambda, mu are leaves of our distributions, and also each one of these leaves is totally geodesic in the screen distribution, and we make a calculate the curvatures of this submanifolds. Okay. So I just arrived to the third part of my talk, and I will speak some words about this work in progress, also with Matias Navarro and Didier Solis. Now we address the following problem. We have a null manifold, say abstract manifold, and the Lorentzian manifold M bar. So we ask, it is possible to give an isometric immersion from M to M bar? In order to answer this question, we have to give some precise statements in the following way. Okay. This slide looks like the ones that I mentioned in the beginning of my talk, but now we will give M as an immersed submanifold into M bar. Okay, so we have M bar, a Lorentzian manifold, M a manifold, and F an immersion. So we induce a metric on M in the natural way. And so we say, as usual, that F is an isometric immersion. But we will be interested in the case where G, where the induced metric, is a degenerate one. So in this case, M is a null manifold. And as before, this is equivalent to have a one-dimensional distribution, the radical distribution, such that every section of this distribution is orthogonal to every vector field in M. We also fix a screen distribution, which is, as before, a distribution complementary to the radical. And over M, we also define this vector bundle, F star T M bar, with fiber the tangent space of M bar to the point FP, F of P. So in this situation, we have a transversal distribution, which depends on the immersion, which satisfies these conditions on the metric. Okay, as before, we say that our conditions here mean that all sections of the transversal distribution are orthogonal to all vectors on M. The transversal distribution is formed by null vectors, and we have some kind of normalization. G bar of F star U B prime is different from 0. So, as before, we have these Gauss-Weingarten equations, but I will not rewrite them. But I will call the attention to these to the curvature equations. So we have now also lots of connections here, 5 connections on each bundle, and we have 5 curvature tensors. We define the derivative of our second fundamental forms in the usual way. Just noting that we have to be careful what connection to choose in these expressions, but we can establish our Gauss-Codazzi equations in this form. Also, we have well, quite long expression for the Ricci equations here, but we may have them without problems. Okay. So this last slide, suppose that we have an immersion of M into M bar. But what happens in the isometric immersion problem? We have all these elements in the slide. We have the null manifold, the screen distribution, the radical distribution. We define a connection nabla on M, which I didn't say before, but this connection is not metric because the metric on M is not a definite one, but restricted to the screen distribution is a metric connection relative to G. We have the Gauss-Weingarten equations, and that's it for M. But we also have to look for some vector bundle, which I called here E, which will play the role of the transversal bundle. Okay. So we have we want to prove this theorem. Okay, we're almost there. We have to discuss some details, but I think that we already have the proof of this theorem. Okay, so let me explain what happens here. We have a null manifold M with a fixed screen distribution. We give, as I said, a vector bundle E, which will play the role of the transversal bundle. We define E bar as the sum of the tangent bundle of M and E, which will be the tangent bundle of our ambient space M bar. Okay, and we define some metric G bar and connection nabla bar over this bundle E bar, which satisfies some compatibility conditions. I didn't want to fill the slide with many details, but we have these conditions, these compatibility conditions. And we also suppose that the Gauss-Codazzi-Ricci equations hold on this vector bundle for the case of R bar equal to 0. Then we may solve this isometric immersion problem. We can give an isometric immersion of the null manifold into the Lorentz-Minkowski space, because we are dealing with this zero sectional curvature case. And we can give vector bundle isometry between our abstract bundle E into the transversal bundle of Tm relative to this immersion, such that this vector bundle relates the second fundamental forms and the transversal connection nabla T with the connection we have in our abstract bundle E. And moreover, this isometric immersion is kind of unique in the following case. If we have two isometric immersions, and if we have a vector bundle isometry between the transversal bundles relative to each immersion, satisfying this kind of, let's say, preserving the second fundamental forms and preserving the connection, the transversal connections, then there is an isometry of our ambient space, which relates our isometric immersions. So the isometric immersions, they are unique, except for some rigid motion in the Lorentzian Minkowski space. So as I said, we have this. We have to clarify some details, but I think that we have this immersion theorem for the case of zero sectional curvature, and of course we will work on also the other cases of a constant sectional curvature. But I think that this one is a nice theorem. Okay. So these are some references. Of course, these ideas on the immersion problem came from one recent book by Marcos Daxer and Rui Tojeiro, and also the classical text for the study of null submanifolds is this one, Dougal Sahin. You know? We also give a list of our papers along the years. Okay, so and I will stop here. Thank you very much.